Okay, so we looked yesterday at a couple of properties of definite integrals, and they were stated explicitly for integrals that are proper. So that's what we had in calculus 1, proper integrals, and now, well, as opposed to improper, the only difference is that the interval might be either not open, not closed, or not bounded. So these are, look at these intervals meaning the integrand. The integrand is, I'm sorry, the intervals of integration is AB. Both A and B are included, so that what makes integral proper. And the integrals that we talked about recently have been improper in the sense that either the interval might be infinite or it might be not closed. So to include all one and put them all together in one place, it's we got to develop a little bit of a terminology, and that will make our life easier. So what I'm talking about is first of all about the intervals. Let's just review intervals that we know. Okay, so some of them are closed, and some are not. And then some are bounded or finite, and some are not, unbounded. So closed bounded is one and only AB. Okay? And now, however, the intervals that are still bounded but not closed, it means that either one end or the other or both are missing. So it's either A, B removed, or A removed, B included, or both of them are removed. Okay, A, B. Okay? So these are not closed intervals that are not closed. Okay, and we are by now are able to handle integrals of over. That's what the last topic is. Those intervals, how we integrate functions over those intervals. Okay, so unbounded are it could be negative infinity A, including A or not including A. Well, no, they're closed, so they're included. And secondly, B infinity, as well as negative infinity. Okay, so these are closed and bounded, and then unbounded, unclosed is negative infinity A, and well, there are the B and A infinity. Okay, so we didn't spend a lot of time on the last one, but the plan is the same pretty much. Is to whatever you encounter intervals of these kinds. So like this one or in the last two, you would have to cut you have to cut the interval in half, or maybe more than in half, in order to deal with proper integrals, because we do know how to handle these. As long as the interval is defined on the whole interval, then you're okay. We know how to handle it. There will be one limit. So one point is missing, and then we know how to. There will be only one limit. Either B goes to either B goes towards the end, or A goes towards the end, and that limit of those intervals gives the improper integral if it exists. Okay, so that's a little table, and so let me use then the notation that I want to use, so that I don't have to every time indicate what I'm talking about. You will use letter I that stands for interval. So I is one of these. It could be any of these, and it is by now we know the meaning of. So I mean the definite integral. Integral over an interval. And once again, unlike calculus 1, we now know how to handle all intervals, not only closed and bounded. So once again, let me point that out. This is Calc 1 over here, and only. The rest, now we have expanded from Calculus 1, we expanded in these directions so that we can handle those two. Okay, so what is the notation? It's very simple notation because the integrals now have one letter. We just put it underneath like this. So that's just notation. So whenever the I is specified, you have to then figure out what to do with it based on these discussions. Okay, so point out whether it's closed and bounded, then there is no trouble. You do Riemann sums. If not, then or just find it here. If it's not open and bounded, closed and bounded, then you have to then do limits in addition. Okay, but the and everything is covered, both the discussion before and after. We did improper integrals, and then the properties are all nicely satisfied because of what we have seen so far. The tools that we have seen are the additivity rule, once again illustrated right here, and we also in fact started with an illustration of that additivity property right there in the middle, how it applies to improper integrals, and it works out just fine as long as we were careful how to write it with this notation. So for example, additivity so integral over I f dx plus integral j f dx. Okay, let's try to figure out what this how we write it properly without referring to a picture, even though the picture certainly helps, but only to come up with an idea of what it means. So we have integral I and integral j. What do we have in the right? Another integral. What I want to merge these two integrals into one. It's just the way I did yesterday. So what do I do? What do I write here? Kinda. There's a better way, not the bad, but the proper way. We don't do addition as numbers or functions. How do we add sets? Remember, what do we call it? It's not sum, but what? How we put together. So this is I, the first integral. The second one is j. What is this, if you remember? What do we call it? Two integrals put together into one. What's the term for it? Or if you remember notation for it? The union? Anyone? Union? The union. This is in green one is the union of I and j. That's the term that used instead of addition. That's what we use for sets. Okay, so we combine them together. Literally, there's no algebra going on. See, so that's why we don't want to say addition. We just take everything that is in I and everything that is j and just put it together. It's like just two bags of objects, and we create one bag for both of them. So that's the union, literally. Okay, so remember that word from before? No? And use, that's right, and the notation is the U symbol. So this is I, U, J. You don't say U, you say union, but still it works out. So that's, and I want to integrate all of this new interval, I, union, J, right? So the one that is in green. Okay, so that was definitely the idea that we had yesterday. We were not speaking of integrals. We didn't call integral I. We called it AB, and so that is just more tangible. And you can AB. That's what we did yesterday. AB union CD. AB union BC is equal to AC. Right. That's what we did yesterday. Remember? We just didn't use this terminology. Okay, so it's not complicated terminology, especially when all we deal with is intervals, and these two intervals produce new intervals, and everything is within the x-axis. That's all. So that works out fine. There is a caveat. There is a caveat. My picture is misleading. Okay, so because this is what I'm saying here, that this is I, and this is J, right? I do draw this way. I illustrate this picture in that way that this is I and this is J, okay? But I didn't write it. So, like I said, the picture is good, but we cannot just entirely rely on the picture. We have to say what we are seeing. So, what are we seeing? What I'm saying is, well, what if the picture was different? What if this was I and this was J? Would the formula still be true? No, why not?
They overlap.
They overlap. The intervals overlap, which means that the area that we are counting, these are areas after all, they will be double counted. Okay, so this is, if there's a function there, then these we're looking at like this. So the area above I is this. The area above J is that. And one piece of the area is double colored, so it is double counted. Okay, so we don't want to deal with that, so instead of, then we have to add that caveat. So in order to, so that we make sure that the picture on the right is what we're dealing with, not what we have on the left. How do we say it? When, what's so special about I and J? How will you describe that picture that I have on the right? On the right. So this is I and this is J, as opposed to what I have on the left. There is an overlap. There is kind of an overlap here, but it is what? Just a single point. Okay, so when the overlap is a single point, we are not concerned about the area, because the area of this line over here is 0, so that's why it does not contribute anything to, even though it is double counted, but you double count 0, it's still 0. So okay, so how do you, so what I'm saying is that I and J have one point in common. There is another term that was used in the past to express this idea of two intervals or sets having something in common. Remember what it was? Just a minute ago we talked about unions, and now we're talking about intersections, right? So we're talking about, I want to ensure that the intersection between I and J is not too large. So that intersection over there, where is the intersection? This is the intersection. The I is red, J is yellow, the intersection is purple, and it is too large. It creates a double counting. So I just have to make sure that that intersection is not too large. And the intersection is, remember the symbol for intersection, it's the same U upside down. So the intersection between I and J is a single point. Okay, so that creates an additivity. So there are some more caveats to be added here, is that certainly f has to be integrable over these two functions to begin with. Well, let me just say f. So f is integrable over I and J separately. Then we have this conclusion about integral, which is integrals, which is called additivity. So if you unite two intervals and then these two, it creates a new integral which is equal to the two integrals that you started with. Okay, so it's really uncomplicated, but if you think about areas, it is really something that you absolutely have to have. I mean, the two areas, they have this additivity property. They doesn't have to be, wouldn't have to do anything with the areas necessarily, just the with integrals necessarily. Integrals, so areas satisfy this property. If the two areas, two regions don't overlap, or overlap very little, then what is the relation between the areas of these regions? Well, this plus that is equal to this, the area. Okay, so area as a number versus the area as a area as a region. So regions and areas. Areas in mathematics we're careful, and when we say area we say we mean a number. Okay, just as length is a number, area is a number, volume is a number. So in that kind of hierarchy, and then we prefer to speak of sets or intervals or regions or something like that. So there would be no ambiguity. Okay, so that is my additivity property. 4, it is applicable, as I said, it applies equally to proper or improper integrals. So, for example, it is possible that these points at the ends are missing, and things still work out. It's fine. Okay, so same thing happens with the sum rule, which I brought up yesterday. Sum rule. So if f, once again, is integrable, f and g, as a matter of fact, this time instead of having two intervals, we have two functions, one interval. If f and g are integrable over interval I, then so is f plus g, and there is a relation between those two integrals, three integrals. F plus g dx over the interval I is equal to integral f dx over integral I plus the same for g. Okay, so integrable meaning means that the integral exists and it is finite. So whenever that case, which when the integral improper integral is infinite, that does not apply here. Not it might. You might tweak the rule a little bit so that you could do some algebra with infinities. But when we say integrable, we mean that these are all of these are numbers. Okay, so infinite integrals certainly are important and worth mentioning. They will come up again later on. At this time, I'll just make one mention of what happens with improper integrals. So once again, f is called integrable over I if its integral exists as a number. We also say that the integral converges. Otherwise, it diverges. Diverges, so that limit, remember the improper integrals that we looked at, diverges means that either the limit doesn't exist, it could be infinite, or it doesn't exist. In general, in that case, we have divergence. So divergence, convergence now is the difference between numbers and not numbers. So then let me just give you examples. So 1 over x is integral 1 over x dx diverges from 1 to infinity. Integral from 1 to infinity 1 over x squared that converges. Okay, so let's see. So I actually did not continue on with more properties here, but you certainly remember the constant multiplier rule, I suppose I should have mentioned. But they're all the same, come from from calculus 1. Here we are moving in a slightly different direction, and that is the distinguishing between diverging and converging limits, or existing, non-existent limits. I'm not sure if you the term diverges was applied to limits, right? The limit diverges. Remember that term, right? So in other words, to say it does not exist, but it's the same word pretty much. It is just more, I guess it's slightly more specific if you say the limit diverges, the limit converges, because you sort of remove the idea of what it converges, what is the limit. If you say it converges, the users say, well, I know there is a limit, I don't know what it is, but it's still a limit at least. So it's useful information, but not maybe not necessarily specific enough sometimes. So the question is, sometimes I just want to bring up one of the examples here is, for example, this. When things get simplified is when this function is positive. So what if f is positive? So what can we say about the integral from 1 to infinity f dx when the function f is positive? So it's look like 1 over x. Okay, so let me write out the definition as we did. So b goes to infinity, integral from 1 to b f dx. Okay, so once again, replaced the improper integral with a proper integral. And now I'm asking, what do you remember about from calculus 1 about integrals of functions that are positive? If the function is positive, what can you say about its integral?
The integral is positive.
The integral is positive, so that's it is positive, yes, but there is more to it. So it's positive, definitely. It's positive, but actually I didn't ask the right question. The right question is, what about the antiderivative? This is an antiderivative. What I'm looking at, this is the antiderivative. Antiderivative of my function f, and the variable is b. Remember the fundamental theorem of calculus 1 of the second version, I believe it is the you take the definite integral and vary the upper limit, which is exactly what we have there, which creates a function, as we just studied this information, and then of that function we have been taking limits, and when the limit exists, that is our integral. But I want to set that aside for a moment and just ask ourselves, what do we know about antiderivatives of positive functions?
They're increasing.
That's right. If the function is positive, then its antiderivative is increasing, because if you reverse the order, then it means that the derivative of that function in green, in circle, is f, right? So it means that the derivative of a function is positive. What do we know about the function? It's increasing. So it's increasing. Okay, so and now we're interested in, so let's call it f capital, this function. Okay, f of b over here. So there was some kind of function f of x to begin with, which was positive, say y equal f of x. Then I created a new function, which is its antiderivative, whatever that is, antiderivative. So y equal f capital of x, antiderivative. So f capital prime of x is equal to f of x. So that's all familiar from calculus 1. What it looks like, as we just established, it is increasing. How exactly, we don't know, but that's what it roughly looks like. Okay, and then remember what, once again, improper integral, what we're after is find, for improper integrals purposes, find limit f of x, x goes to plus infinity. That will be our integral. That integral over here that we're looking at is the limit of the antiderivative at infinity. Okay, of this particular antiderivative. It just happens, remember there are infinitely many antiderivatives for each function, that's what plus c is. But if we pick one particular, and we did, because how did we make the integral, the antiderivative particular? We chose the lower limit. We fixed the lower limit, which means that, in fact, f of 1, what is f of 1? Look carefully at the picture. What's in green, in the green circle? If b is equal to 1, the integral is 0. Okay, so it starts here at 1, it starts at 0, and then it just grows. Okay, okay. And then we're looking for its limit, and when that limit exists, we say that that's our integral, but another possibility is that limit does not exist. However, what is we know that the function is increasing. What did I say? Okay, f is increasing. So the question becomes, what do we know about its limit at infinity of a function that is increasing? So a function is increasing, so it does not oscillate. Remember those bad examples we considered earlier this week, the functions that oscillate, and then the outcome of such a limit might be really bad. It could be just sine function, for example, nothing really bad, but the limit doesn't exist. But when the function is increasing, then there are only two possibilities. What is it equal to? It's either infinity or a number. So it's not like sine function. There are only two possibilities. One of them is certainly is kind of negative, but the function either go like this to infinity, or it starts to slow down and flattens out and has a horizontal asymptote. Okay, so which means that is good news. Why? Because first of all, you can add infinity to infinity and get another infinity. Another one, you can compare one function to another and find out whether or not functions like this, and they will be then we can say something about the outcome. Let me do it once again. What we did, we did it last time. Let's do it again. So suppose we know, and we do, that integral 1 over x 1 over x is from 1 to infinity is infinity. Okay, so now let's consider compare to integral from 1 to infinity 1 over x power of s here, s less than 1 but larger than 0. Okay, so we have one integral that is familiar to us at the top, and we create a new integral with a bunch of integrals. I want to make as many conclusions as I can about these integrals. The answer you might already remember. We looked into that. Remember what the answer is? Well, that doesn't matter. The point is, it will be based on the comparison of the two functions, which will produce the comparison of the two integrals. Okay, so let me compare. So 1 over x is this. Okay, and where is the other one? So this is 1 over x. Where is the other one? Above or below? Well, just compare x, 1 over x versus 1 over x to the s. If you flip, you will have x, s, and x. So as an example, you can think of s as 1/2. Okay, it will cover pretty much. It gives you the idea of what's going on. So which one is larger, x or xs? X or square root of x? Which one is larger? X is larger, right? Because we're looking only to the right of 1 anyway, right? So square root will be less. So which means, what does it mean about the reciprocals over here? Which one is larger? 1 over x or 1 over xs?
Reciprocal.
Yeah, they're reciprocal. I'm moving backwards here.
1 over xs.
That's right. So when we take reciprocal, we flip the sign. Okay. So that it means that x 1 over xs, the second function, its graph will be lying above the first one. So this one will be here. 1 over xs. Okay. So now both functions are positive. Okay, so both of them positive. So then we know that there are only two outcomes. Well, we already know the outcome for the first one is infinity. The only two outcomes for the second one are infinity or a number, a positive number. Okay, which one is it? In other words, does it converge or diverge? What? It does. Why? How do you know? Well, ask yourself, what is the meaning of the first integral? What is the meaning of this integral? On the graph. What should I do on the graph to explain that? Integrals, definite integrals, all represent what? The graphical interpretation of the definite integral is the area. The area, even if it might be infinite area, it's still the area. So that's the area of the graph of 1 over x is that integral. So remember, that's what we talked about this week. This area is, in fact, that integral, and it is infinite. Okay, so this area is infinite. Okay, the second integral now also represents the area. Okay, the area under the other graph. Okay, so this is what it represents, right? All the way to the green curve. Okay, so
you're trying to figure out the area in between those two lines?
no, I didn't know. Actually, no. I'm trying to figure out the area of the yellow area. Period. No, not the difference. No, just what is the area, yellow area? Yes, but let's just look at the picture. It is the yellow area contains the purple area. The purple area is infinite, so greater than infinite makes it infinite, right? So this one is infinite too. That's the conclusion that we make. So that's how comparisons work. So they only work for positive functions, so that there would be no oscillation, the ability to run away. But it is they are when there are only two options, either positive infinity or a number, and you know that whatever that is cannot be a number because it's larger than infinity, or it is larger. It is definitely larger than infinity. Then you conclude that it is infinity. So let me state this comparison theorem. So f and g are integrable over integral I. Once again, could be finite or infinite. Okay, and positive. F and G are positive. Okay, then, so that's given. Well, no, the third condition is the actual comparison. Where's that thing? Hold on, where's that? There it is. So the first condition they are integrable. Second condition they are positive. The third condition there, f is less than g over I. Just like that graph over here. Okay, so both graphs lie about the x-axis, but g lies higher than the other one. So then, well, let me put a larger than or equal to here. Integral over I f dx less than or equal to integral I g dx. And as just to make that point, both could be infinite. Okay, so the property itself you must have seen in calculus 1. It is just comparison of limits, and you certainly can imagine that you just take that picture over here and cut it like this, forget about the tail, and concentrate on one finite graph, and then it's entirely within calculus 1 situation, and the comparison theorem. You must remember at least a little bit of that. They once again comparing two functions. One, the it's like a sandbox, and if the level is higher, then one level is higher than the other, then the amount contained is also higher. Okay, so the function represents the height of your sand, and then the area, the integral represents the amount of sand contained in that particular sandbox. So if then the top, if you see that wherever you look at the level is higher than the other, then the amount of whatever is inside the sandbox is higher. So that's what the integral says, the property says. And then, but then we also, in addition, what we brought in addition to that, now that the integrals might be improper. Okay, so to begin with, so you can have infinite areas or functions undefined at the endpoint of the integral, something like that. But as long as they are well, yeah. That's not what I said, unfortunately. So integral means that it is a number. So integral means that these two numbers are comparable to each other. But in addition to that, what the example suggests, that it still works even though one of the integrals is infinite. Okay. So and that's the conclusion that we made. What did we do? We discovered that our function f was infinite. Okay. So we started with integral of f is equal to infinite. Then we concluded that g is also infinite, because something that larger than infinity is also infinity, roughly. That's a rough idea, okay? And that works out for certainly when we reverse the opposite situation. The opposite situation is, well, let me give you an example of the opposite situation. It is the integral of 1 over x squared dx and integral 1 over x cubed. Okay, so dx. So both of them, once again, both functions are positive, so it means that the integrals will be either number or infinity. Okay, so then also we can compare the two functions. I did the same thing. Sorry about that. What I meant is over here I want a 3. Okay, which one is larger? Which one from the function is larger? 1 over x squared or 1 over x cubed? On the integral from 1 to infinity, which one is larger? X squared is larger because x cubed is larger, so they're reciprocal, just following the same logic. Then, once again, we have a comparison of functions, therefore we have a comparison of integrals. Okay? Okay, so let's try to use the same idea, but the conclusion will be different. So what's the conclusion we can draw about it? We know what the integral. This one is known. What do we know about the integral on the left? We talked about it a couple of days ago. Is it, well, all we need to know is it, well, not what it, is it divergent or convergent? It is convergent, and this is how I can write it. So there are only two possibilities. It's a number or it is infinity. Since it's a number, I just could say that it is less than infinity. So at least it's one way to write it. You can just say, in other words, this integral converges, which means that it's a number. What that number exactly doesn't matter, but it is a number. Okay, so that we know. What do we conclude now about the other integral?
That one also converges.
It also converges, right? Why? Because it cannot be infinite, right? There are only two possibilities: infinity or a number. It turns out it's not infinite. Okay, then it is a number. It converges. Okay, and then you can do the same with any power, as long as this power is larger than 2. In fact, anything that's larger than 1 will work out and produce a convergent integral. The dangerous place here is to draw conclusions about too strong conclusions from unjustifiably. So I could try to use the same logic in what if I look at 1 over x? 1 over x dx is larger than 1 over x cubed. So the one on the right, on the left, diverges. This one diverges, as we know. I'm sorry, the inequality, yeah, okay. So what can we conclude about the other integral?
It's either infinity or a number, since it's less than the one that diverges.
What you said is correct, but so can you wrap it up or summarize what you have discovered? So you said it's either infinite or a number. Okay. So what's the conclusion? What's the positive information that you have derived about it?
It's going to have a maximum number that it can be.
No, what you said was correct. You just let's evaluate the what we have achieved with this conclusion. The integral on the right is either convergent or it's not convergent. Okay, so what's the value of that? There's no value. There's no value to it because there's really nothing you can conclude from this. So this one is infinite. So all you have demonstrated that your integral under investigation is less than infinity, less than or equal to infinity, let's say, which means that it could be a number, it could be infinity. So, well, okay, so it doesn't really help us. So, so the answer to the question is nothing. So we already knew from the beginning, without the involvement of the first integral, we already knew that the second integral is either convergent or infinity. And we know as much as before. So it depends on what you compare with. If you demonstrate that your function is less than a function the integral of which converges, like over the first example, then you can conclude that your function also has a convergent integral. But if it is less than an integral of the function, the integral of which is divergent, the second example, then nothing you can say about it. So it's like if you once again look at the picture, so the similar picture, but imagine that the purple, let's say let's imagine that the green one is infinite, or the yellow region is infinite, hypothetical. If the yellow region is infinite, what can we say about the purple region? Nothing. So it's just less than it's what could be inside of an infinite region could be infinite or could be finite. We don't know. So it's not helpful. That's all we can say. And vice versa. If I'm looking at this picture once again and I say, suppose the purple region is finite, what can I say about the yellow region? Nothing. So the purple region is finite, and the other region is bigger, so it may be a little bit bigger, maybe a lot, so it could be infinite once again. So you don't know. So you have to be, you have to know, you have to really, if you do a comparison to say function f, you really have to know that something about its comparison and about its convergence, and then do it, take it in the right direction. So if it doesn't work out, you have to know that I draw no conclusion over here, I do no conclusion here, and then, okay, so I now realize that it's not helpful, so I might try to compare 1 over x cubed with something else, and it turned out to be what I compared with. I compared it with 1 over x squared, and suddenly I do have a conclusion, so that thing does converge. Okay, so that's the things about when you deal with improper integral. It's possible to have infinities, and then you have to manage infinities appropriately, which will come up later on in this course. We are wrapping up this part of the course, and the last part of the course will be about series, and once again, infinities, infinite summations, and we'll face a very similar situation. At this point, what we're turning into is applications of definite integrals and things such as so that we'll go beyond the most familiar to you applications, or at least that as far as I know, these are the only two that really are being discussed, and that is applications of it is the area and the displacement. Well, actually, let me start a new one. Okay, so its official name is applications of integrals, but really we're going to be it's much more than that. So applications of integrals. So we certainly start with a review of what applications we already know, and one just came up recently. If y equal f of x is velocity as a function of time, right? Velocity is a function of time. So x is time, y is velocity. Then the integral from a to b, fx dx, is what? The position, or I'd say the displacement. It's the change of position is the displacement, right? Change of position or displacement from time x equal a to during that period of time to x equal b. Okay, so that's number one of very big applications. The big application goes all the way back to Newton. Okay, so where it came from. So that's a big deal, obviously. But the second one is also from Calculus 2, and that is the integral represents the area. Okay, so we'll be coming back. Either one or the other is helpful whenever you don't understand something about the integral. Use one or the other as something tangible to help you out. Hopefully, is the area under the graph of y equal f of x from a to b. Let me put it in a more precise terms. Under the graph, this is what the wording that was used in Calculus 1, but if you want to be more careful, this is how you put it. The area between the x-axis, the graph of y equal f of x, and two lines, line x equal a and line x equal b. Right, like this. AB. So the vertical line, horizontal line, the x-axis, and the graph, and that gives me the area. Applicable to both of these, if you're careful, you apply the idea of we're thinking about two possibilities. First of all, x could be negative, right? Or at least some values of x could be negative. So whenever the graph of f dips below the like this, below the x-axis, then remember what happens. What happens to the area?
Is it a negative area?
So yes, this counts as a negative area. The same for interpretation number one. It means that you're moving in the opposite direction. Negative velocity, moving in the opposite direction. Okay, to begin with. So that's how you can end up with a negative area. So we're talking about a signed area. It's possible that it could be negative. Another way to end up with a negative area if A and B are flipped, and so it is possible that A could be larger than B. Pretty much the same thing. It's like a displacement from 1 o'clock to 2 o'clock. That's one thing, and the displacement from 2 o'clock to 1 o'clock would be the opposite sign, right? And the third possibility, what is the third possibility is no, that's it. That's it. So the upper limit could be lower than the lower limit. Okay. So it is very much easier to explain these ideas for when you're talking about motion, because negative velocities are really not a big deal, but the negative areas, it takes a little bit of thinking. Okay, so I'll just see you next week then.